In this video, we are going to learn about different indeterminate forms that we may happen upon when trying to evaluate a limit, and a technique called L'Hopital's rule that we can use to evaluate them. So if you think back towards the beginning of this course, we were evaluating limits. And we learned that when evaluating limits, the first thing that we should try is direct substitution. Try direct substitution and don't run into any issues, then we have an answer for our limit. However, if we run into an expression such as 0 over 0 or infinity over infinity, we have landed at an indeterminate form. And these are indeterminate forms because we are not able to determine anything about that limit. If we get 0 over 0 or infinity over infinity, it doesn't tell us that the limit exists. It doesn't tell us that the limit does not exist. And if the limit does exist, it doesn't tell us what the limit is. Now, we have seen several examples where we evaluated a limit with direct substitution. We got 0 over 0, and we were able to algebraically manipulate that expression, such as finding a common factor and canceling it out, so that we were able to finish evaluating the limit. But in some cases, we are not able to do that. So let's look at some examples. In example 1, if I attempt to evaluate this limit with direct substitution, we have 2 multiplied by negative 1 squared minus 2 over negative 1 plus 1, which leaves us with the indeterminate form of 0 over 0. I could then work on simplifying this expression. I'll factor a 2 out of the numerator. And then I can factor the quadratic that's in the numerator. And once we factor that quadratic, we can see that we do have a common factor of x plus 1 that we are able to cancel out. And we are left with a form, an expression, that now we can evaluate using direct substitution to get our final answer of negative 4. In example 2, if I were to try to evaluate this limit with direct substitution, the numerator would go off to positive infinity and the denominator would also go off to positive infinity. But we learned a technique that we can come into this limit and divide each of the terms by the highest power of x that we see in the denominator, which is x squared. So I've divided both of the terms in the numerator by x squared, and I've divided both of the terms in the denominator by x squared. Now some things cancel out, leaving us with 3 minus 1 over x squared in the numerator, divided by 2 plus 1 over x squared in the denominator. Now, if we apply the limit to what we're left with, the terms that have x squared in the denominator are going to go off to 0. We've seen that before, leaving us with simply 3 over 2. Moving on to example 3, if we first start off with direct substitution, we have e to the 0 minus 1 divided by e to the 0 minus 1, which leaves us with the indeterminate form of 0 over 0. However, we can factor the expression in the numerator because it is a difference of squares. I will point out that e to the 2x is the same thing as e to the x quantity squared. So the numerator factors into e to the x plus 1 multiplied by e to the x minus 1. Then we see that we can cancel out the common factor of e to the x minus 1, simply leaving us with e to the x plus 1. Then we can apply direct substitution, be left with e to the 0 plus 1, which leaves us with a final answer of 2. So examples 1, 2, and 3 were all examples in which we were able to do some kind of algebraic manipulation in order to arrive at a simpler expression that we were then able to evaluate with direct substitution. In this lesson, we're going to learn, well, what can we do when we are not able to do this algebra to simplify our limit and get an answer? For example, if I look at a variation of number 3, so I still have this e to the 2x minus 1 in the numerator, but now in the denominator I only have x. Notice that if I were to factor the numerator the same way that we did in number 3, it would not be helpful. And the reason it would not be helpful is because we're not able to cancel out any common factors. Now, we have learned other techniques besides algebraic manipulation in order to evaluate a limit, such as evaluating a limit numerically using a table, or evaluating a limit graphically by looking at the graph. In both cases, we can see that the limit appears to be 2. However, we are now going to discuss L'Hopital's rule, which gives us a way to evaluate this limit without using a table or without using a graph, but instead using calculus. So L'Hopital's rule says that if you are evaluating a limit and direct substitution yields an indeterminate form of 0 over 0, or any combination of positive or negative infinity over positive or negative infinity, that you can then rewrite the limit by taking the derivative of the numerator and the derivative of the denominator. I want to be very clear here that what's happening here is not the quotient rule. We are not applying the quotient rule. We are simply taking the derivative of the numerator over the derivative of the denominator. And then we can again try direct substitution. And perhaps this expression would give us something that we could then evaluate the limit with. The nice thing about L'Hopital's rule is that if you apply this rule and you end up with this expression and direct substitution still does not work, you can do it again. So in other words, I'm saying you could then come in and apply the limit where now you have the second derivative in the numerator over the second derivative in the denominator. And we can do this as we need to until we are able to evaluate the limit. So now let's try example 4 using calculus and L'Hopital's rule to evaluate this limit. We've already discussed what happens if we try direct substitution. If I substitute in, I end up with e to the 0 minus 1 divided by 0, which is the indeterminate form of 0 over 0. Now, it is important to first try direct substitution because you can only use L'Hopital's rule if you end up with one of these indeterminate forms. We can see we have 0 over 0, which is a valid indeterminate form for us to try L'Hopital's rule. And so now I'm going to come in and take the derivative of the numerator. The derivative of e to the 2x is 2e to the 2x. Make sure you're using the chain rule there. The derivative of 1 is simply 0. And in the denominator, the derivative of x is just 1. So now let's try direct substitution again. We would have e to the 2 times 0. And that's multiplied by the 2 in the front. I don't have to write the 1 that's in the denominator. This leaves us with 2 times 1, which is equal to 2, which is verified by the numerical table and the graph that we looked at. So this is how L'Hopital's rule works. Notice that I did not use the quotient rule to take these derivatives. I simply took the derivative of the numerator and I took the derivative of the denominator. I then applied direct substitution. Because we ran into no issues, we were able to finish evaluating our limit. Now let's look at example 5. If we were to attempt to evaluate this limit with direct substitution, as natural log goes to infinity, as x goes to infinity in the natural log function, we go off to positive infinity. And as x goes to infinity in the denominator, we go off to positive infinity. This is a valid indeterminate form in order for us to use L'Hopital's rule. And if you're going to use L'Hopital's rule, I need to see which indeterminate form you landed at when you tried direct substitution. So now let's begin to apply L'Hopital's rule, which says that we can take the limit as x goes to infinity of the derivative of the expression in the numerator divided by the derivative of the expression in the denominator. The derivative of natural log x in the numerator is simply 1 over x, and the derivative of x in the denominator is just 1. So now we are just left with the limit as x goes to infinity of 1 over x. And because the denominator has a higher degree than the numerator, this limit goes to 0. So we've already discussed that we can use L'Hopital's rule for indeterminate forms of 0 over 0 or positive infinity over positive infinity. And remember, it doesn't necessarily have to be both positive infinities. You can use it on any combination of positive or negative infinity divided by positive or negative infinity. But those are not the only types of indeterminate forms. 0 times infinity, 1 to the infinity, infinity raised to the 0, all of these are other types of indeterminate forms. Now, to be clear, we cannot use L'Hopital's rule on an expression that generates one of these indeterminate forms. We would need to do some kind of manipulation so that we are looking at one of these indeterminate forms, those for which L'Hopital's rule are valid. So now let's look at an example where we have to do a little bit of work before we are able to apply L'Hopital's rule. When I look at example 6, direct substitution would lead us with e to the negative infinity times this infinity, because as x goes to infinity, the square root of x would go to infinity. E to the negative infinity would be going to 0. So this is really giving us the expression 0 times infinity. And by the way, I know that this would be going to infinity because technically you could think of that as 1 over e to the infinity. The denominator is getting very large, and so the entire fraction is going to 0. We are not able to apply L'Hopital's rule because this is not one of our indeterminate forms for which L'Hopital's rule can be applied. So we're going to begin by first rewriting this limit as the limit as x goes to infinity of, we have the square root of x, and let's rewrite this e to the negative x. Because the exponent is negative, I can write it as an e to the positive x in the denominator. Now, if I were to apply direct substitution, we would have the indeterminate form of infinity over infinity, which is a valid indeterminate form for us to apply L'Hopital's rule. So now we begin with L'Hopital's rule, which means that we're going to come in and we're going to take the derivative of the numerator, which would be 1 divided by 2 square root x, and the derivative of the denominator, which would be e to the x. Before I jump in with direct substitution, let's first just simplify this expression. We have a fraction divided by e to the x, so I'm going to be multiplying by the reciprocal to be left with 1 divided by 2 square root x e to the x. Now, if I were to apply direct substitution, the denominator is getting very large, and so the entire fraction is going to 0. If I start off with direct substitution on example 7, on the inside, we're going to have 1 plus 1 over infinity, which is essentially just going to give us 1. Because we know that 1 goes to 0, and then in the exponent, that's going to infinity, so we're left with 1 to the infinity. Now, this is an indeterminate form that L'Hopital's rule cannot be applied to. Particularly with this infinity in the exponent, we're going to need to get a little creative with how we evaluate this limit. So the first thing we're going to do is we're going to assume that the limit exists, and we're going to call it y. Now I'm going to apply natural log to both sides of this equation. Because natural log is continuous on its domain, we are able to switch out the natural log in the limit. So I now have the limit as x goes to infinity of natural log of 1 plus 1 over x to the x power. Now that I have this natural log on the inside next to that expression raised to the exponent, I can apply properties of logarithms and use the power rule to bring that exponent of x down in front of the logarithm. Now, if I were to try direct substitution on the right side, we would end up with the indeterminate form of infinity multiplied by 0, because 1 over x goes to 0 and natural log of 1 is 0. So I'm now going to do an algebraic technique to rewrite this so that it looks like an indeterminate form that we can apply L'Hopital's rule for. I'm going to keep this natural log of 1 plus 1 over x in the numerator. However, instead of writing x, I'm going to rewrite that as a 1 over x in the denominator. So essentially it was an x to the positive 1 in the numerator, and I rewrote it as an x to the negative 1 in the denominator. And the reason that I did that is because now if I apply direct substitution, we have the indeterminate form of 0 over 0. So now we are able to use L'Hopital's rule in order to evaluate the limit on the right-hand side. L'Hopital's rule tells us that we're going to need the derivative of natural log of 1 plus 1 over x. Generally speaking, recall that the derivative of natural log of u is u prime over u. So the denominator of this will simply be 1 plus 1 over x. And the numerator will be negative 1 over x squared. I took the derivative of 1 plus 1 over x. So I know what's going to be going in our numerator. And then in the denominator, we'll need to take the derivative of 1 over x, and the derivative of 1 over x is negative 1 over x squared. So now let's continue with what we have. The negative 1 over x squared in the numerator and the negative 1 over x squared in the denominator can cancel, leaving us with the limit as x approaches infinity of 1 over 1 plus 1 over x. If I were to try direct substitution on the right-hand side now, this 1 over x would go to 0, and I would simply be left with 1. So we have now that natural log of y is equal to 1. Remember, we started this problem off and let y be the limit that we're trying to evaluate. So now we need to solve this equation for y. If you think back to pre-calculus, I would need to use the natural number e on both sides to cancel out the natural log and leave me with y is equal to e. So this limit gives us a final answer of e. Example 8. Notice that we again have this x in the exponent. That may be an indication that we're going to have to do something similar to what we did in example 7, where we have to introduce this natural log. So if we start off and apply direct substitution, we are left with the indeterminate form of 0 over 0. I do have that in the exponent, so I'm again going to assume that the limit exists, and I'm going to call it y. I'm then going to take natural log of both sides. And then because natural log is continuous on its domain, we can interchange the limit and the natural log. The whole reason that we introduce natural log is because then we can use the power rule for logarithms to bring that exponent of x down in front of that log. If I were to try direct substitution now, we would end up with the indeterminate form of 0, which comes from directly substituting into the x factor. And if I substitute 0 into this expression, I'm left with natural log of 0, which is approaching negative infinity as we approach 0 from the right. If you're unsure, look at a graph of what natural log of sine x looks like, and you'll see that the graph has a vertical asymptote when x is equal to 0, and that graph is approaching negative infinity. The graph looks something roughly like this, at least that piece. And then there's another piece over here, so there's a VA right there. You can see as we approach 0 from the right, that graph shoots down to negative infinity. This is not an indeterminate form of which we can apply L'Hopital's rule, so we're going to need to do a little bit of algebraic manipulation to arrive at one of the indeterminate forms to which L'Hopital's rule can be applied. I'm going to rewrite this factor of x as a 1 over x in the denominator. Now, if I were to apply direct substitution, we would have the indeterminate form of negative infinity over infinity. Think about what the graph of 1 over x looks like. That's a parent function from pre-calculus. This is an indeterminate form to which we can apply L'Hopital's rule, and so now we begin to apply it. Taking the derivative of the expression in the numerator, the derivative of natural log sine x, think about the u prime over u rule. In this case, u would be sine, so that's what we would have in our denominator. And in the numerator, the derivative of sine is cosine. So we have cosine over sine, which is equal to cotangent x. And in the denominator, the derivative of 1 over x is a negative 1 over x squared. I'm going to simplify this expression before I apply direct substitution to see if we're now able to evaluate the limit, because I can write this as a negative x squared divided by tangent x. I essentially just took the cotangent and sent it to the denominator as its reciprocal, and I took the negative 1 over x squared and sent it to the numerator as its reciprocal. Now, if we were to apply direct substitution, we would land with the indeterminate form of 0 over 0, which is a valid indeterminate form for us to be able to apply L'Hopital's rule. So now we take the derivative of what we have in the numerator, simple power rule, leaving us with negative 2x, and we take the derivative of what we have in the denominator, and the derivative of tangent is secant squared. Now, if we come in and apply direct substitution, we get a 0 in the numerator and a 1 in the denominator, which leaves us with a final answer of 0 for natural log of y. Remember, we started this problem off by letting the limit that we're trying to evaluate be y. So now, in order to finish solving for y, I need to apply the natural number of e to both sides of this equation to see that y is equal to 1. In example 9, we again begin by applying direct substitution to this limit, which would leave us with the indeterminate form of infinity minus infinity. Again, if you're not sure, I encourage you to look at a graph of both of these functions individually and ask yourself what is happening on that graph as x approaches 1 from the right side. To help us arrive at an indeterminate form to which we can apply L'Hopital's rule, I am going to combine the difference of these two fractions using a common denominator. In this case, the common denominator would be the product of x minus 1 multiplied with natural log of x, and in the numerator, we would have x minus 1 minus natural log of x. Now, let's apply direct substitution again. In the numerator, we would have 1 minus 1 minus 0, which gives us 0, and in the denominator, we would have 0. So we do have an indeterminate form to which we can apply L'Hopital's rule. So we're going to take the derivative of the numerator, which would leave us with 1 minus 1 over x, and the derivative of the denominator. Now, in order to take the derivative of the denominator, we're going to need to use the product rule. And we're going to use f prime multiplied by g, to which we add g prime multiplied by x. And that is what we will have in our denominator. Now let's apply a little bit of algebra to simplify this expression before we try direct substitution again. I'll leave the numerator. Actually, what I'm going to do to simplify this, because I want to get rid of these fractions within fractions, so I'm going to come in and multiply everything in this expression by x, which will leave us with x minus 1 in the numerator and x natural log of x plus x minus 1 in the denominator. Now let's apply direct substitution again. In the numerator, 1 minus 1 would leave us with 0. And in the denominator, natural log of 1 is 0. And then 1 minus 1 is 0. So we have the indeterminate form of 0 over 0. Let's apply L'Hopital's rule again. The derivative of the numerator is simply 1. In order to take the derivative of x natural log x, I'm going to need to use the product rule, where I would have f prime g added to g prime f. The derivative of x is simply 1. Simplifying this, we have the limit as x approaches 1 from the right of 1 divided by natural log of x plus 2. As x approaches 1 from the right on the natural log function, we approach 0. And we are left with our final answer of 1/2. So far, we've spent a lot of time talking about indeterminate forms, and we've seen several examples of them, but there are also determinate forms, which means that if you arrive at those forms, you are able to conclude what the limit is equal to. Here we have several examples of determinate forms, and they tell us what that limit is actually equal to. And we have another reminder that L'Hopital's rule can only be applied to quotients that lead us to an indeterminate form of 0 over 0, or any combination of positive or negative infinity divided by positive or negative infinity. In example 10, let's look at another example. If we start off and apply direct substitution, we end up with the indeterminate form of infinity over infinity, which does tell us that we can apply L'Hopital's rule. I'll take the derivative of the numerator. The derivative of e to the x is simply e to the x. And in the denominator, the derivative of x is 1. Now I can apply direct substitution, and we know that as x goes to infinity on e to the x, we get infinity as our answer. In example 11, I'll again begin with direct substitution, which would leave us with the indeterminate form of infinity over infinity as x goes to negative infinity. That is an indeterminate form to which we can apply L'Hopital's rule. So I'll take the derivative of the numerator to get a 2x, and I'll take the derivative of the denominator to get a negative e to the negative x. Now direct substitution would give us a negative infinity over a negative infinity. So I'm now going to again apply L'Hopital's rule. The derivative of 2x in the numerator is simply 2, and in the denominator, the derivative of negative e to the negative x is a positive e to the negative x. And now as x goes to negative infinity, the denominator is getting very large, and so our limit is equal to 0. And then finally, example 12, if we start off with direct substitution, we yield the indeterminate form of infinity over infinity. And so we're going to rewrite this limit using L'Hopital's rule by taking the derivative of the numerator, which will be e to the x, and the derivative of the denominator, which is 1 divided by 2 root x. Before I apply the limit, I'm going to take a little bit of time to rewrite this expression so that we have 2 root x multiplied by e to the x. Since we're dividing by a fraction, we can multiply by the reciprocal. And now if we apply direct substitution, we simply arrive at infinity for our answer.